Welcome once again. This module discusses shifted gradient series, both arithmetic and geometric. We assume that you have watched and mastered the previous module on equivalency calculations for shifted uniform series and isolated single cache flows. We'll start with an arithmetic gradient series. That's the one that changes with a constant amount, capital G, every period. This is a conventional gradient. The constant increase of G first appears in year 2, and it continues through year n. The present worth, indicated by P sub 0, is located 2 years prior to the start of the gradient, that is here in time t equals 0. There's a base series. It's called A for each year, and it occurs in years 1 through n. It's important to remember that the gradient series and the base series must be accounted for separately when you're using engineering economic factors, such as the PG, PA, and PF factors. However, when using a spreadsheet, the functions like NPV for present worth or PMT for equivalent uniform amount will consider the gradient and the base amount together, so there's no need to separately enter the values of the gradient and the base amount. What about a shifted gradient? Well, it will start at any time other than year 2, but the present worth will always still be 2 years prior to when the gradient starts. Here is a shifted arithmetic gradient. It has a base amount in the years 5 through 8 and a gradient started in year 6. The timelines have been labeled as actual years from 0 through 8 and gradient years from 0 through 4. Gradient year 2 is the same as actual year 6. In the general case, to use the factors, there are 4 steps to find the total present worth, which we'll label capital P sub t at time t equals 0. So follow along with the steps as we perform the calculations. First, as with the conventional gradient, we'll find the P sub g 2 years prior to when the gradient starts using the PG factor, as mentioned here in step 1. Second, we'll move that P sub g value back to year 0 with a PF factor. Third, we'll work on the base series. We'll use the PF and the PA factors to find the present worth at time t equals 0 of the base series. And finally, we'll add those 2 values in time 0 to get the total present worth, P sub t. Here's a numerical example. The base is $100 per year in actual years 5 through 8. And there's a gradient, the amount of $30, and it begins in year 6 and goes through year 8. And you see the gradient years indicated here. We'll use the 4 steps to find the present worth in year 0. First, we use the PG factor multiplied by the $30 gradient for 4 years, and we get $139.50. Secondly, we use the PF factor as indicated here in step 2, and we move back to time 0 to get $102.54. Third, we'll find the present worth in time t equals 0 for the base amount. Notice here there are 2 factors. There's the PA factor for 4 years, and then there's the PF factor to go back from year 4 to year 0. That's $243.45. Finally, we add the 2 together, and we get basically $346 as the present worth amount in time 0. Now let's turn our attention to determining an equivalent uniform series. That's an A value. We'll call it A sub t, and it's for the same shifted gradient. One way to find A sub t over the periods from 1 to 8, which we show in red arrows here, is to use the AP factor at 8% for 8 years for each of the P values. And we have to do this for the gradient and the base series. Well, this method is shown in a progressive fashion. First, we find the A sub g for the gradient. Notice the AP factor at 8% for 8 years. We get $17.84. Secondly, we find the A sub B for the base series, that's taking the present worth value we found before of $243, multiply by the AP factor, and we will get $42.36. Finally, we add these two and we get the total amount of $60.20 as the equivalent uniform annual amount for years 1 through 8 for this uniform series, base series and the shifted gradient. Now there must be a simpler way to do this, right? Right. Look at this. It's the same cash flow series that we've been analyzing. So what do you think might be a one-step method to find the A sub t for years 1 through 8? Think about it for a couple of seconds. If you answered to multiply the total P sub t value in the year 0 by an AP factor for 8 years, then you're correct. Or you might have answered that you would multiply the future worth in year 8 by the AF factor for 8 years. That's also correct. So you can work from one end or the other. So let's work from time t equals 0 and use the AP factor and perform the computation. If we do, we take the $345.99, multiply it by an AP factor, and we get $60.20, the same amount as we did before. The discussion thus far has covered arithmetic gradients. How about geometric gradient series, where the series changes by a constant percentage, small g, each time period? Again, the present worth is going to be, P sub little g, is going to be located 2 periods prior to when the gradient starts. But now the initial amount, A sub 1, is included when the PAGIN factor is used. Thus, there is no base series considered separately. And this is the same as was summarized in an earlier module that you probably watched. Take a look at this geometric series, which has some additional cash flows. There's a $35,000 investment in year 0. There's a $7,000 series, but let's not call it a base amount, but it goes from years 1 through 13. And there is a increasing gradient where little g is equal to 12% per year, and it starts in actual year 6. We will use the sequence, and I equals 15%, to find two numbers. First, the P sub g value in gradient year 0, which is actual year 4, and then we will find the total P sub t value at time t equals 0. Here again is this cash flow diagram, and we've summarized the values, the important values, below. You can see here little g is 12%, interest is 15%, the value of the ongoing uniform series is 7,000, and the n value for the gradient is 9, and that's in actual year 13, but gradient year 9. To find the total P sub t, first of all, we will use several factors. We will use the PA factor for the $7,000 series, and that's for years 1 through 4. We will consider the $7,000 that is in year 5 as the A1 value for the geometric series to get it started. Then we can use the PA 12, 15, 9-year factor and the PF factor to come back to the present through the 4 years to get to time 0. After we include the present worth amount of $35,000 that was already there, you see that the total amount is $83,232. So that's the present worth for the investment, the uniform series, and the increasing gradient at g equals 12%. We should make a quick comment about working with negative or decreasing gradients. For a decreasing arithmetic gradient, A is the largest value in the series of cash flows, and the G is minus. You would use a minus G in the computations for the PG and the AG factors, and the present worth P sub G is still located 2 years before the first gradient appears. To find the present worth at time t equals 0, use the PF factor with n equal to the number of periods between P sub G and t equals 0. If it happens that the geometric gradient is decreasing, The procedure is the same as before, except a minus G is used in the computations. But the P sub G is still located 2 years prior to when the percentage gradient appears, and the PF factor is used as it was in the arithmetic gradient. As a final consideration of this module, the speed-up factor that is offered by spreadsheet functions to perform equivalency calculations is demonstrated. Here is a relatively complex cash flow series for which we will determine the present worth P sub t at time t equals 0. We'll use I equals 8%. First, we have a series that we'll call the investment series. It is a decreasing arithmetic series. It starts at minus $7,000. It decreases, the investment decreases, that is, $1,000 each year, and it goes through year 5. The amount that has been invested earns interest at 8% per year through year 11 when a withdrawal series starts. The withdrawal starts at $20,000 in year 11 and is reduced by 20% each year and stops in year 15, which is gradient year 5 for this decreasing geometric gradient. Now, what is the question? Are the 5 investment deposits earning at 8% per year sufficient to cover the anticipated 5 withdrawals? In other words, was enough money put in, and did it earn enough at 8% to be able to cover the intended withdrawals? We'll use a spreadsheet-based present worth analysis to determine if there is an overinvestment or an underinvestment. Here's the spreadsheet. It shows the years, it shows the cash flows of the entire sequence. Note that the 0 entries in years 6 through 10, when the investments will be accumulating monetary value, have been entered to be sure that the time dimensions are taken into account in a correct fashion by the spreadsheet functions. The functions are listed in column C, so here you see the decreasing arithmetic and here the decreasing geometric gradient functions. Next, we'll apply the NPV function to find the present worth in year 0. You'll see that it is $5,130. The NPV function that's detailed here takes into account the entire series from cell B4 to B18, which is the years 1 to 15. And of course, the beginning point has a value of 0, but cell B3 needs to be included. What does this $5,130 indicate? Well, it has a plus sign in front of it. So, will the investments cover the withdrawals? Think about it for a second. You should have answered no. Why? Because the plus sign on the present worth value means that the withdrawals have a p-value of $5,130 more than the present worth of the investments. So the conclusion is that either more investments are needed or less withdrawals should be planned. Or alternatively, the money could stay in longer between the investment and withdrawal series. Well, it completes the summary of shifted gradient series. Together with the earlier knowledge you've gained from the conventional gradient computations and these computations here in this module about shifted gradients, you should be able to tackle virtually any cash flow series that includes about any type of gradient that is constantly changing by an amount or a percentage from one period to the other. Hope you have enjoyed it and it has been helpful. Thank you for watching.